Swayam Prabha. Digital India. Educated India.
I already told you that vinegar, or acetic acid. Vinegar is about probably 2% or 4% of acetic acid in water is vinegar. But acetic acid is used for making is a raw material in industry to make various different kinds of compounds. And methanol is one of the raw materials that is available. And if you want to convert that methanol into acetic acid, by incorporating a carbon monoxide into this, you need a catalyst, and here is a rhodium catalyst, and that method is called Monsanto acetic acid synthesis. Looks very simple, acetic acid, but making that is not simple. You cannot simply combine methanol and carbon monoxide without any catalyst and make an acetic acid. You cannot do that. But that is done using catalyst here. So this is the company which came up with that method, and then maybe there is a table somewhere showing you that how many or how much of these compounds are made in what scale. So these are all made in millions of tons every day. So that means they have so much of applications. So polymerizations. Here is for example, if you want to polymerize a simple, so N-olefin, that means it can contain many other different kinds of groups. And then you can control the polymerization and property, many things, using here is an aluminum, that is what is used, but various other transition metals compounds are used to control the property of the polymer, PET and many things I showed you, different kinds of polymers I showed you. So if you want to make different kinds of polymers with different properties, then you need to control the polymerization using a metal. And for example, catalytic converter, motor vehicle, underneath if you notice there will be this kind of a small unit that will be present, that will have it's called catalytic converter. That means when the combustion happens, when the petrol gets converted to energy and carbon dioxide, which happens at very high temperature, and during that process it also converts small amount of nitrogen into nitric oxide and all that, which is not good for the atmosphere, right? Also these petrochemical products, small amount of sulfur will be present, they are slightly soluble, so sulfur also gets converted into sulfur dioxide and trioxide and all that. So if you let all those into the atmosphere, then ozone layer will get depleted. So you don't want that to happen. So to prevent that, those chemicals not coming into the atmosphere, like N oxides, they are called NO2, NO3 or N2O2, various different kinds of N oxides which are not good for the atmosphere, so they will deplete the ozone layer. So to prevent them, there is a catalytic converter which converts that N oxide into nitrogen, right? Or sulfur dioxide into sulfur trioxide, which will react with water and forms sulfuric acid. All those molecules will also absorb heat, and then it will be too hot, the atmosphere becomes too hot, so you don't want to let them into the atmosphere. So what is that? So these are, you see here so many motor vehicles which are everyday consuming petroleum products, and during the process, because this combustion happens at very high temperature, if you touch the front of the engine of a car, you will see it will be very, very hot. It is because this combustion happens at very high temperature, and at that temperature these parallel reaction also happen. because nitrogen is present in 80%, around 80%, right? So some of them do get reacted with oxygen, and at high temperature these kind of molecules also get produced along with the carbon dioxide, and you don't want them to be in the atmosphere because they will deplete the ozone layer. So this rhodium, platinum is what is present in this catalytic converter. That is one of the reasons why car is expensive, because this catalytic converter, because these are noble metals which are very expensive, and they are present in this catalytic converter. That's why it is called catalytic converter. They are present in small amount, so that's why they are catalyst. But these are very, very expensive, and the role of them is to convert these molecules into less, because oxygen and nitrogen is present in the atmosphere, so no problem. You don't want NO and then NO2 to be there in the atmosphere. Yeah.
Same. Efficiency of the exhaust.
Efficiency of
Exhaust, because exhaust works with the exhaust itself. So when the catalytic
when the exhaust is hot, it easily the gases come out, right? You don't want to freeze them.
Like even if it's hot, the engine. That is
No, fans, all that is taken care of. Fans will be definitely present to dry them out. Huh? So basically, what I am trying to emphasize is the presence of the metals, transition metals here. So where and all they have applications, what I am trying to show you. Okay, and so I was telling you that this is the table that shows how much of these materials, chemicals that are produced every day. For example, sulfuric acid. So 35 billion kilos are prepared. So ethylene, polyethylene, propylene, phosphoric acid, ammonia, benzene, urea, nitric acid, and you have studied nitric acid, for example, or sulfuric acid, how it is prepared, you have studied, right? So all of them require transition metals, a catalyst to sulfur dioxide to sulfur trioxide, not in a simple reaction. So you need a catalyst. So V2O5 and all that you have studied, right? If you remember still. So this is just to show you top 20 industrial chemicals produced. This is a long time ago. This is probably multi-folds now. Is only to illustrate that such simple chemicals require transition metals. So hence studying of quantitative chemistry or transition metal chemistry is important. If you understand the chemistry, then you understand their applications also. So that is the reason, the why study the chemistry of transition metals, which I have illustrated with various different kinds of examples to show you that they have applications. Okay, so let us. So I'll just briefly show you these transition metals. Before I go to the role of metal ions in biology, you also want to understand that what is the nature of these compounds, transition metals, right? So why it is called transition metals? If you look at the left side of the periodic table, which are S block elements, and right side of the periodic table, which are P block elements. So S block elements and the two ends, if you combine, then you will form ionic compounds. Sodium chloride, for example, right? Or lithium chloride, lithium bromide. So these are salts which are ionic nature. But the one on the P block, for example, combining carbon and carbon, so which are covalent in nature, right? Carbon monoxide is covalent nature. So ionic, covalent, and it's a new bonding in the case of transition metals. So there is a transition in bonding. Ionic, covalent, and these coordination compounds are neither ionic nor covalent. So there is a transition. So hence they are called transition elements. Understood why they are called transition elements, and also why they are called coordination. So that means in the case of ionic compounds, so sodium, for example, gives full electrons to become sodium, and then Cl becomes Cl minus. So complete transfer of electron happens. Whereas in the covalent compounds, sharing of electrons happens. Whereas in this coordination compounds, only one gives electron and other accepts electron. So that is where the coordination comes. That's why these are called coordination compounds. So there is a difference in the way the electrons are transferred. In one case completely transferred, in another case the equally shared, but here the electron, it's not covalent in nature. Transition metals are not covalent. Ionic, covalent, and neither covalent nor ionic, the transition metals, and that is why that name transition. So those compounds, that's why these three different kinds of names are used. Coordination means ligand. So here they have a definite shape and geometry. These transition metal compounds have a definite shape and geometry. So what are those shape and geometry? So many metal that so far I highlighted, transition metals, if I go back to the first slide where I showed you the periodic table, and then in the center of the periodic table is where the transition metals are present. Scandium, titanium, vanadium, manganese, iron, all the way to cobalt, nickel, copper, and then zinc. That those are the 3D metals, and then you have 4D metals, and then 5D metals. You have so many transition metals, and so these M refers to one of those metals. Transition metals can be scandium, titanium, vanadium. So then you have manganese, iron, cobalt, nickel, all that, right? And I also told you that in these coordination compounds, metal ions are not present. These are the ionic compounds, not like they are not in the metallic state. Metallic state, metal is in the zero oxygen state, whereas here in the ionic state, so that metal has an oxygen state of +1, +2, +3, whatever the oxygen state possible or stable oxygen state possible for that metal. Most of the transition metals have a common oxygen state of +2. Some of them have +3, or manganese, for example, has +2 to 7. So 3 and 4 also is known. So various different kinds of oxygen states are known for transition metals. So some stabilizes +2, some stabilize +3, some stabilize 7. Not all of them stabilize 7. So various different kinds of oxygen states are there, and so that means these are oxidized in the oxidized form. They are the those compounds formed by these ionic compounds or coordination compounds or transition metal compounds.
Sir,
Yeah.
could you explain what a coordinate bond is again?
Huh?
Could you explain what a coordinate bond is again?
I'll tell you. Did I chalk somewhere? Yeah, let me just initially show you what it is, and then I'll tell you what is coordination means. See, if you take sodium chloride, sodium is sodium metal. So that means sodium plus and then chloride minus, right? So this charge separation this is what is ionic. But if you take CH4, for example, methane, or any organic compound, carbon containing, carbon monoxide, anything that if you take, these are covalent. So that means C and H, because of the electronegativity difference between the carbon and nitrogen, is a bond that forms, which is so the sharing of electrons, this is what happens between the carbon and nitrogen. So this is covalent. Whereas this is ionic. So in the, for example, if we take copper ammonia, complex, where copper is in the +2 oxygen state and ammonia are coordinated. So for the compounds to function as a ligand, they have to have a lone pair of electron. So nitrogen has a lone pair of electron, water has 2 lone pair of electrons, right? So these lone pairs are donated to metal. So if you show it with a bond, an arrow, that refers to coordination bond. But in the textbook, not necessary that all of them will be showing the, but we know, we have understood already, in the case of transition metals, there is a coordination bond and supposed to be showing this arrow. So that means this pair of electron is given to metal which is in the +2 state. So we always put the charge on the metal outside the compound. So this is copper ammonia complex, and then so the pair of electron on the nitrogen, what is there, is donated to copper 2. So copper 2 has to have vacant orbitals for it to accept electron. So in this case, there is a sharing of between the hydrogen and in the carbon, there is a sharing. But in this case, there is no sharing. Completely ligand is giving electrons to the copper. So this is what is called coordinate bond. But here, this is 100% transfer has happened, but here not necessarily be 100%. So that is the difference between ionic, covalent, and then coordination bond.
So in the case of an ionic bond, it's an ion, but in this case, it's like a lone pair alone that is being done.
Given, yeah.
So what is the definition of a ligand?
What is that?
Ligand. Definition of a ligand.
That's something that has a capacity to provide a pair of electrons. Anything that you take, yeah.
Is the coordinate bond always involve a ligand?
Huh?
Does the coordinate bond always involve a ligand?
Coordinate refers to always metal complexes. So that means it has to, the ligand has to provide a pair of electron. For example, if water is protonated, let us say protonating, so it forms a, so that it doesn't have now lone pair of electron, so it doesn't function as a ligand. Ammonia, for example, I protonate it and make it NH4 plus. Now that lone pair of electron is gone. So ammonium plus cannot function as a ligand. So ligand is a molecule, an organic or inorganic group that has a pair of electrons to give. It can have more than one pair. So water has more than one pair, right? Chloride has more than one pair. Cl minus, for example, if we take, has more than one pair of electrons. So around that octet rule, it has to, so that means there should be 8 electrons around the molecule, then only that will give you stable molecule. So here also there will be 8 electrons, so that means more than what is pair of electrons are present. So they can function as a ligand. So ligand is a group, can be inorganic or organic, that has a pair of electrons. Minimum 1 pair of electrons has to be there, it can be more than 1 pair of electrons. So water has a 2 pair of electrons. So water also, copper aqua complex, for example, six or 4 copper, if you take a copper salt and add only water, now water is a ligand. But now if I replace this by ammonia, then I get this complex, copper ammonia complex. This is pale blue, this is dark blue. So the color also depends on what is the kind of group that is present around the metal, and those kinds of groups are called ligands. So here is the simple ones what I am showing you, is it can contain copper, I have written here 4, I have written here 6, and you can see there various different kinds of numbers are present around the metal. So that is decided by the nature of the ligand, decided by the nature of the metal. So it is like in a bench, normal size, if we take only 3 people can sit, but if they are too small, not very fat, 4 people can sit. But if it's too fat, only 2 can sit. So same method is applied here, same concept is applied here. So it depends on the size of the ligand, depends on the size of the metal. And so you cannot have around the metal n number of groups. So number of groups are also fixed. So that is determined by the nature of L and nature of M. And normally what you see here on the left hand side, you see, so there are 6 groups around the metal, and the way that they are arranged here is called octahedron. That is the shape of the geometry, which is called octahedron. That means there are 8 faces. So you can see 1 face, 2 face, 3 face, 4 face. So there are 8 faces. If you count, there will be 8 faces. That's why it's called octahedron, but has only 6 groups around it. So this L is it can be L can be water, can be ammonia, it can be Cl minus, or it can be Br minus, or I minus. So these are all the groups that I have written. They are all inorganic, but I can have so this is ethylene diamine is organic, right, but still has an amine group. So that amine nitrogen can have 3 bonds around it, right? That is what ammonia has, 3 bonds around nitrogen, but with a lone pair. So there is a lone pair here, and there is a lone pair here, and those 2 lone pairs can coordinate. So these are the these are called monodentate ligands. Dentate means dental, that means like a tooth. So you can, so 1 tooth or, here. So that's why these are called, this is a name called dentate, denticity, bonded to the metal through a pair of electron is called denticity. So if this has an ability to give only 1 pair, this also has an ability to give 1 pair. So these are all called monodentate ligands. But if I put if I join these 2 together, for example here, ethylene diamine, then this becomes a bidentate, because through nitrogen, now I can, metal. So I can put another one on this side. So NH2, and that is what is shown here. So here if you notice,
Sir, for the complex ion that we discussed right now, so is the complex ion that we discussed right now using copper and
complex has?
The complex ion that we discussed right now using copper and ammonia, so there the hybridization will be square planar, sir?
Not square planar, in the textbook that's what they say, but copper can never be square planar when the +2 oxidation state is there. That you will learn later.
Okay, sir.
It depends on what is called as a Ann-Taylor distortion, something and all happens.
Okay.
So is always copper 6 coordinate.
Okay.
But the other 2 are very weakly coordinated. So in the textbook those are neglected, and hence made it to appear like a square planar. They are actually not square planar, but some textbook do say they are square planar, but they are not. And that's why I did not write here another 2 ligands.
Okay.
But otherwise, it is always copper has a majority of the simple ligands. But if you use complex ligand, then you can control the geometry.
Okay.
Complex in the sense, if they are sterically bulky, if they hit each other, so all of them cannot come in the same plane, then they go in the opposite direction and becomes tetrahedral, and is what it is here. So when the size of this and the size of this is too big, they hit each other. So instead they rearrange, so the tetrahedral will be this fashion. So 2 are like this. So this is square planar. Assume that I have a bidentate ligand, this is square planar. But then if there is a bulkiness, so they hit each other, they cannot sit in the same plane. So instead they go like this, which is what is tetrahedral.
Sir, but usually in square planar, we tell it a square planar even though there are lone pairs there, right? So if there are lone pairs, still there will be repulsion. So how do they like go back to tetrahedral even if they are bulky groups?
No, lone pair has to be there. Without lone pair,
Yes, sir, there will be repulsion, right? So how will they form tetrahedral either ways?
no. This is the metal complex where VSCPR theory doesn't work. Metal complex VSCPR theory doesn't work. It is only for small molecules.
Thank you, sir.
Is it a stacked system or stacked system? Is it a stacked system? I mean, ethylene.
What is you are saying? Stack. What is stack?
Are they in the same plane or are they like in sheets?
Even they are in the same plane, you are asking. If it is square plane, they will be in the same plane.
So it is the size of the ligands that decides whether it's square planar or tetrahedral.
Size of the ligand is big, it is tetrahedral. Because they will hit each other. If they come in the same plane, its size is big, so they will not agree to occupy the same space. So it goes this way then. Then the repulsion will not be there. That is what is tetrahedral. So I've written here to show you that all this structure bonding and all that you have learned. Hybridization no longer is applicable to transition metals. So it doesn't explain everything. So there is a failure in explaining so many properties of transition metals. So that's why later is a different theory called crystal field theory that comes. You'll probably study that. So VSCPR theory or then hybridization and all that you have studied is applicable to simple molecules. But not applicable to transition metals. You probably be able to say this hybrid based on the geometry, whether it is a square planar or tetrahedral. I will be able to say what is the hybridization, but that doesn't tell us whether it has that kind of a geometry. So because I already know what is the geometry, then I can tell you what is the hybridization. But in the unknown system, in these cases, you will not be able to tell. And that will not tell you whether it is a paramagnetic, diamagnetic. Properties are also magnetic property because they contain lone pair of electrons. So if the lone pair electrons are present, they are paramagnetic, and if there are no lone pair electrons, they are diamagnetic. So through hybridization, sometimes you can say whether it is diamagnetic, paramagnetic, but not all the time that is true.
So since tetrahedral structures will always be more stable than square planar structures, why do square planar structures exist? Is it only because there's like lone pair bond pair repulsion, or?
Can you repeat that question again?
A tetrahedral structure will always be more stable than a square planar structure because
it is the other way.
wouldn't the bond pairs be further apart so there'll be less repulsion?
No, in terms of forming a geometry, the size is determined. But otherwise, square planar is preferred. But it is not possible because of the size. But otherwise, square planar is much more stable than the tetrahedral.
So why is that, sir? Because wouldn't they be closer together and face more repulsion?
That is why there is what is the theory will explain that. But I will not be able to probably explain you the theory. Crystal field theory will tell you why it is that. Is a theory like what you have, VSCPR theory, and hybridization, all that you have learned, right? So similarly, to explain the transition metal complexes, the structure bonding property like color or why they are paramagnetic, diamagnetic, to explain all that, these theories fail. You will not be able to predict based on these theories whatever that you have learned. Yeah.
Sir, When we saw the structure of sulfuric acid, we actually saw that the S in the sulfuric acid is hypervalent. Is there a coordinate bond in sulfuric acid structure?
Sulfuric acid, as
Because
such,
I saw some people saying that the S has two coordinate oxygen bonds and two normal oxygen covalent bonds.
see, sulfuric acid cannot bind because I'll tell you, H2SO4, only if it is SO4 2 minus, that means if it is say salt, then only it will coordinate. Acid will not allow it to coordinate because it will protonate the ligands.
No sir, like in the structure of sulfuric acid.
Sulfate can coordinate. Sulfate has a tetrahedral geometry. This kind of a geometry, so it can coordinate. It can coordinate.
Sir, also like probably not related to this, but we have compounds made by xenon, like xenon compounds like XeF2, XeF4. How does that work, sir? Probably not related to coordinate geometry.
Xenon compounds, to make xenon compounds itself is very difficult. They can be made, but those complexes containing metal are very rare. Because if you see, xenon and all will be in higher oxidation state.
Sir, but how do they form the bonds, sir?
Which one?
Like XeF2 bonds and stuff.
That those can be synthesized. People thought in the beginning they are all highly inert, but intervalent between the halide itself compounds, between the inert gases and then halides compound, they can be made. You need that's why they form with highly electronegative elements like fluoride or oxygen sometimes.
What?
Huh?
What is the bond?
Which one? In the case of
Inert.
Between two inert gases.
inert gases is always van der Waals. Inert gases is always van der Waals. Okay. Yeah.